Uh, okay. Welcome to the last class of this problem solving session of heat transfer course under the guidance of Professor Dasgupta and myself Kalpita Nath. I am research scholar at IT Kharagpur. So it's like we'll wait for some more time, at least 5 minutes for others to join, and then we'll start with today's session. So yeah, till then, let's wait for 5 minutes. Okay. Okay, so today we'll start with firstly previous day's problem. So previous day 5 problems were left to be solved. So we'll start with that. So this is the first problem. That's question number 9 of previous class, where zero point 0.6 kilos of water per minute is passed. That is the mass flow rate, and it's passed through a tube of 2 centimeter diameter, and it's found to be heated from 20 to 6 degrees Celsius. The heating is achieved by condensing steam on the surface. So there is a phase change at the surface. That means it is a constant surface temperature question that we have already done in convection, right? So and subsequently surface temperature is maintained in 90. So the constant, remember that concept of constant surface temperature. There were two conditions in convection, right? One is constant surface temperature and constant heat flux. So this is the as phase change is there, so this is constant surface temperature question. So use that equations. Determine the length of the tube required for fully developed. So these are the values that are already provided. So based on the equations that we used at that time, we'll be using the same equation here and solve this problem. So yeah, I'll give you 5 minutes for solving this, then we'll proceed with the solution. So we should solve this problem now. So first, as it's already said that the mass flow rate is already given. So mass flow rate is already given. So this is rho AU. So velocity will be m dot upon rho A. So this is 0.01 upon 995 is the density. And area is pi by 4, 0.02 square. Velocity is 0.031 meter per second. Now, let us first determine the type of flow. So, velocity is given. So, we'll find what? We'll find the Reynolds number. Dt by nu. So, this will be 0.031 into 0.02, 0.657 into 10 to the power minus 6. So, this is 943.6. Therefore, Reynolds number is less than 2300. The flow is laminar. Okay. Now, if the flow is laminar, what we'll be using? We'll be using, like, for laminar flow, for constant surface temperature, Nusselt's number is 3.66. This we have already done in our convection part. So we are just remembering all those concepts and formulas that we have already used earlier. So Nusselt's number is also equal to hd upon k. So this is h into 0.02 into 0.628. This is equal to 3.66. So h will be is equal to 144. Sorry, not 144. This is 114.9 watt per meter square Kelvin. So the heat transfer is equal to mcp delta T. So this is 0.01 into 4178 into 60 minus 20 by mcp delta T. This is 1671.2 watt. Now Q is equal to HA delta T. We already know. H we already found out. So area will be pi dl. So this is 1671.2 by mcp delta T. This is 114.9. This is 114.9. Now into pi into 0.02 into L into 90 minus 40. Therefore, length of tube L is equal to 4.62 meter. This is what we needed to find out, right? Now, I hope you have already understood the problem. Now, we'll proceed to the next question. So, what do you need to determine? Radiation heat loss from each meter of 20 centimeter diameter heating pipe when placed centrally in the brick duct of square section 30 centimeter side. Okay. A brick duct square section 30 centimeter each side is there, and a heating pipe is placed centrally in that. With each meter of 20 centimeter and radiation heat loss in each meter of 20 centimeter heating pipe, the length of the heating pipe is 20 centimeter, and we have to find W per meter, right? Now the temperature of the pipe surface is 200 degrees Celsius and brick duct is 20 degrees Celsius. The emissivity of the pipe surface is 0.8 and brick duct emissivity is 0.9. Assume only radiation heat transfer between pipe and brick duct. If the system is in steady state condition, then find the surface heat transfer coefficient of the brick duct, assuming the temperature of the surrounding duct is 10 degrees Celsius. Assume only the brick duct emissivity is also given as 0.9 and pipe surface emissivity is 0.8. The temperature of the brick duct is 20 degrees Celsius and of the pipe surface is 200 degrees Celsius. Assume only radiation heat transfer. We have to find the radiation heat transfer per meter. If the system is in steady state condition, then find the surface heat transfer coefficient of the brick duct, assuming temperature of the surrounding is. Here we have to find the heat transfer coefficient. That means we have to assume the convection as well. So let's solve this problem. I'll give you 5 minutes to solve this, and then we'll proceed with the solution. Okay, so about this, first of all, let us draw the diagram. So this is the duct. This is of 20 centimeter, and this is at temperature T1, and this is at T2. This is 30 centimeter, right? Now, using the formula, Q is equal to sigma A1 T1 to the power 4 minus T2 to the power 4. Right, this formula we already know. 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1 A1 upon A2. Okay, so now T1 is equal to 200 plus 273, that is 473 Kelvin. T2 equal to 20 plus 273 is equal to 293 Kelvin. Now epsilon 1 is equal to 0.8 and epsilon 2 is equal to 0.9. A1 is equal to pi dl, and this is the surface area of the 1 meter pipe, and this is equal to pi into 0.2 into 1 is equal to 0.2 pi is equal to 0.626 meters. And A2 is equal to perimeter into length. So perimeter is 4 into 0.3, right? 4 into 0.3 into 1. 4 into 0.3 into 1. There is also the surface area of 1 meter duct. That's why length is 1 meter. Now, okay. Now this will be 1.2 meter square. Now Q is equal to 5.678 into 10 to the power minus 8.626 meter square into 4.73 to the power 4 minus 2.93 to the power 4, 1 upon 0.8 plus 1 upon 0.9 minus 1. Into 0.626 upon 1.1187. If T3, now for the second case, if T3 is the atmospheric pressure, then Q is equal to A2H T2 minus T3. As here, convection will be taking place. So H is equal to Q upon A2 T2 minus T3. So this is 1187 upon 1.220 minus 10. This is 98.9 watt per meter square degree Celsius. Okay, so this is done. Now we'll proceed to the next problem of previous day. A polished metal surface of 5 centimeter outside diameter and 370 Kelvin temperature at the outer surface is exposed to ambient condition at 295 Kelvin. The emissivity of the surface is 0.2 and convection coefficient or heat transfer coefficient is 11.35. That stage is 11.35. Calculate the heat transfer by radiation natural convection per meter length of the pipe. Take thermal radiation constant, and what would be the overall coefficient of heat transfer by the combined mode convection radiation. Same, you will directly apply the formula. There is nothing to explain. It's the similar fashion. So I'll give you 5 minutes to solve this, and then we'll proceed with the solution. So let's solve this problem now. So about this, the surface area of the pipe meter run is equal to, now the surface area we have to find out, that will be pi dl. That means pi into dia is 0.0535 centimeter into L. L, that is per unit meter, we have to find out. So this is 1, L will be 1.157 meters square. Q radiation is equal to epsilon sigma B A T1 to the power 4 minus T2 to the power 4. Right? Now QC is convection HA delta T. This it will be this is 0.2, this is 5.67 into 10 to the power minus 8, this is 0.157, and T1 is 370, T2 is 295. So this will come about 19.88 watt. Now HA delta T, this is 1.35 into 0.157 into 370 minus 295. This is 133.64 watt. Now Q total is equal to 19.88 plus 133.64 watt, that will come out to be 153.52. Now we need to find the total we need to find out the overall coefficient of heat transfer by combined mode of radiation. So coefficient of heat transfer means U, overall heat transfer coefficient, that is U we need to find out. So we already know that QT is equal to UA delta T overall. So U will be Q total upon A delta T. So this is 153.52 upon 0.157 is the area, 370 minus 290 delta T, 295, right? So this will come out to be 13.04 watt per meter square degree Celsius. So this is in Kelvin. So here is the answer. Let us proceed to the next question now. A long homogeneous resistance wire of radius not of 0.6 centimeter and thermal conductivity is 15.2 watt per meter Kelvin is being used to boil water at atmospheric pressure by the passage of electric current. So electric current is sent and it is heating the water up. Heat is generated in the wire uniformly as a result of resistance heating at the rate of, so Q is given, Q upon area is given. Okay, Q per unit volume is given. The heat generated is transferred to the water at 100 degrees Celsius by convection with average heat transfer coefficient is given, assuming steady one-dimensional flow. Heat transfer, the temperature at the central line of the wire is given by. So simple, it's electricity is passed, it is heating this, and heat is given, heat that is passing from the electrical wire per unit volume is given, and the heat transfer to water is at 100 degrees Celsius, and the heat transfer coefficient is also given, assuming it is one-dimensional flow. What we need to find out, the temperature at the central line of the wire, at this temperature we need to find out. So yeah, I'll give you 5 minutes for this and then we will proceed with the solution. So let's proceed with the solution of this question. So first of all, heat generated from the electric wire will be converted. So heat that is generated will be converted in convection. So this Ts from here, Ts is equal to T infinity plus Q R naught by 2H. So this is 100 plus 16.4 into 10 to the power 6.6 into 10 to the power minus 2. This is 2 into 3200. Now this will come out, surface temperature will come out to 115.375. The temperature at the central line of the wire, that is T naught, this will be Ts is equal to Q R naught square by 4K. This formula we already have used for convection inside a pipe. This we can easily calculate. So now this will be is equal to 16.4 into 10 to the power 6 into 0.6 into 10 to the power minus 2 whole square, 4 into 15. So this is 9.710. T naught is equal to 115.375 plus 9.710 is equal to 125.0 degrees Celsius. I hope you have understood this. Now for the next question, this is very simple and very easy question. A fin surface is considered of root or base area 1 meter square, and fin surface area 2 meter square is there, and the average heat transfer coefficient is given as this, and effectiveness of the fin is also given as this. If the fin surface of the root and base at 50 degrees Celsius is transferred heat to the fluid at 30 degrees Celsius, then the rate of heat transfer from the fin is. Try to find this out. This is a previous gate question. So this is very easy. Like it will take 30 seconds to solve this. However, I am giving you 2 minutes to solve this, and we'll proceed with the solution. Okay. So about this problem, so heat transfer within the fin, it's very easy that it is question number 30, right? Emissivity into heat transfer coefficient into the area of the base of the fin and the temperature of the base of the fin to infinity. This is the standard formula that we already know. We'll just add the emissivity over there. This formula we already know for the fin, right? So this will be the rate of heat transfer with the fin. So the it's effectiveness, right? So effectiveness will just add on. We already know this formula. So effectiveness into the rate of heat transfer. This will just add on. So this will be the heat transfer coefficient is for 20, and the area of the base is already given as 1 meter square into the base temperature is 50 and fluid is 30. So this will come out to be 320 watt. Yeah. So let's proceed to the next question. In a countercurrent heat exchanger which has been in service for quite some time due to formation of scale, the heat transfer rate is reduced to 85% of this original value based on the clean surface. If the clean overall heat transfer coefficient is 500, determine the value of the fouling factor. So we have to find out the value of fouling factor. So what we can do here, so first of all, the fouling factor we need to find out. So the Q has decreased to at 85% now. So if Q original we have taken, we don't need to even calculate. So it will just reduce to 0.85 of that. Right now, this will be is equal to this overall heat transfer coefficient previously was 500. Now it is 500, 1 upon 500. The resistance will be 1 upon like u something new. Now the previously the resistance was the resistance of 1 upon u. Now the resistance is 1 upon u plus some resistance. So that R we need to calculate, right? You understood. Initially, when it was a clean surface, the overall heat transfer equation 1 upon u was the resistance that we already know for the clean surface. Now when fouling factor is added, 1 upon that u plus the fouling factor resistance R, that will be total be giving some resistance. So that is the total resistance. And now if we find out as the ratio of Q, the initial Q was if we consider as Q, this is reduced by 0.85. Now it is directly the Q. See, the QA delta T ln. That means Q is directly proportional to U, right? And as area and delta T, the temperature, log mean temperature difference will be same only, right? So Q is directly proportional to U. So initially it was Q upon 0.85 of Q now. So this is directly proportional to, initially it was 500 and finally it was some U new. Now you knew from that we'll get. Now finally we got some that this u will be calculated. So this is u new, this is the final one upon 1 upon u 1 upon u initial, that is 500 in this case, plus some resistance. These are we can clearly calculate. So I'll give you 2 minutes to calculate this. I've already told you how to solve this, then we'll proceed with the solution. Yeah. Uh, okay, I think we should solve this then. So I've already explained you. So here, let me give you the values. So U new will come out to be 425. So here it will be 425. So R we can get. So R will come out to be 3.53 into 10 to the power minus 4 meters per Kelvin upon. This is the so we are done with previous day's question. We have more 45 minutes. We can continue now. So we'll solve today's question. So this is the first question for today. Here there is a V group that is 10 mm. This machine and this is machined on a block that is maintained at 1000 Kelvin. If the group surface is a diffuse and gray with emissivity of zero point 0.6, determine the radiant flux leaving the group to the surroundings. So from the group, so we can like consider it a triangle, half triangle, and we can get the length for that, and based on length, we can uh, find out the radiated flux, right, by finding out the area, right. So let me give you a bit idea how to solve this. Like we'll consider this surface, this top surface. Like let me draw it out for you, explain it to you. Just 1 second. So what we'll do, like let's suppose this is the groove, right? So this is the groove, and this is the point. This is 40 degrees Celsius. So this is Q1 from this surface, Q1. Now let us consider this to be a surface. Like let me take some other color. This to be a surface. So this area will be A2, temperature T2 0 Kelvin as is given. So it's there is no temperature over here, right? There is a temperature on this. There is no surface at all. This is just an imaginary surface. So epsilon 2 is 1 for that. This is a hypothetical surface. Now, for this surface, temperature is given as 1000 Kelvin for this surface, and epsilon is given as 0.6. Now, this group it is 10 mm. So in hypothetical surface A2 with temperature T2 at 0 Kelvin is defined. So this we have just removed. So the net radiation that is leaving the surface 1 with area A1 is Q1, right? This we have already thought about, and will pass through the surroundings from two surfaces and pressure and vertices. So this Q1 is equal to minus Q2. This will be in opposite direction, and it will be equals because this is like an enclosed surface. Now this will be sigma T1 to the power 4 minus T2 to the power 4 upon 1 minus epsilon. This all formula we already know. Epsilon A1 plus 1 upon A1 upon 2 plus 1 minus epsilon 2 epsilon 2. Now A1 F12 is equal to A2 F21. We already know that about the view factor. We'll use this and just F21 will be is equal to 1, obviously. From surface 2 to 1 it will be is equal to 1. It is enclosed, and it is like view is completely like surface 2 is completely visible to surface 1. So F21 is equal to 1, and from that we can clearly calculate like if we consider this as a single triangle. Let me use some color. If we consider this a triangle, then what we can do, this is like if I consider this here, this is 20 degree, right? So if this is L and this is X, now like 10, this 20 degree is equal to L by X, right? So now this L we need, right? So this L will be is equal to sorry, this x we need, this L we have, is 10 mm. So this x we need, so x will be is equal to L upon 10, 20, right? Sorry, L upon x. So this, yeah, so this x is equal to L 10, 20. Yeah, so this L is equal to x. Yeah, so this there will be, so x will be is equal to L 10, 20, and this x is equal to L 10, 20. So this will be is equal to 2x we need, the whole surface. This will be is equal to 2L 10, 20. Now this is considered, yeah. Mm, this will be cot. So this is opposite to 1 upon 10. This is cot. Yeah. So this is already done. Now we'll similarly, if we'll do for considering this surface, this will be also is equal to m. If we consider this as m, we consider this as m, then m is equal to 2l cos 20. Now we can consider A2. This is A2, area 2 upon area 1. This is equal to 2L 10, 20 upon this area 1 will be is equal to 2L by cos. So this we can directly put here and we can calculate Q2 upon A2. Q2 upon A2. Sorry, Q1 upon A2. Q1 upon A2. Q1 upon A2 only we need the per unit area. The radiant flux. So heat that is radiating per unit area. So we can clearly calculate this. Okay, so I'll give you 2 minutes to solve this and then we'll proceed with the solution now. Let us proceed with the first part now. So as I've already said, this formula will be applying. Now, epsilon 2 is equal to 1 as we have already hypothesized. So from reciprocity theorem, A1 F12 is equal to A2 F21. And F21 is equal to 1. So A1 upon A1 upon A2 sorry, A2 upon A1 is equal to F12, right? So we can use the reciprocity theorem. So we can directly use this formula, as it is equal to F12. So this I've already said how we got this. Now we'll just put in the main formula. So Q1 upon A2 we are writing. So this is sigma T1 minus T2 to the power 51 to the power 2 to the power 4, and 1 minus epsilon 1 A2 upon A1 plus 1. So now A2 upon A1 is we already found out as this. So this will be, if we sort this out, this will be sine 20 degree. Therefore Q1 upon A2 is equal to 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. 1000 to the power 4 minus 0 to the power 4 Kelvin to the power 4, while minus 0.6 upon 0.6 sine 20 degree plus 1. So this will be is equal to 46.17 kilowatt per meter square. Now for the part 2, we need to find out what evaluate the effective emissivity of the cavity. So the emissivity of the cavity is already defined as the radiant power that is leaving the cavity upon the black body, upon if it is considered to that of a black body area of the cavity opening, like similar black body. So this will be the part 2 will be emissivity if you consider as this. So this is Q1 upon area. So this is emissivity to the power T1. That means this upon sigma T1 to the power 4. For black body, the sigma T1 to the power 4. So this is 46.17 into 10 to the power 3 watt per meter square upon 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4, 1000 to the power 4 Kelvin. So this will be equal to 0.81. Let us proceed to the next question now, because we don't have much time left. So two concentric sphere of diameter d1.8 and d2.2 meter are separated by an airspace and having surface temperature of d1 400 and d2 300 Kelvin. If the surfaces are black, choose the closest value of net rate of radiation between the spheres. So yeah, we can consider this a black body. So we'll just use Diffin-Boltzmann law to find out the we can use the net rate of radiation, the equations that we already know. So okay, so for this we'll just be using the Stephen-Boltzmann law for the first part. So because this is a black body, so for the second part, what is the net rate of radiation between the surface if it is diffuse and gray? So for that the formula that we already used here, this formula, this one will be just using this, right? And for the third case, net rate of radiation heat exchange, just diameter will be increased, so we can calculate for that as well. Emissivities are already given, so I'll give you 2 minutes for 5 minutes rather for solving this, and then we'll proceed to the solution. There are many more questions left, so we have to hurry. We don't have much time left. So first point is that as for your reference, draw a surface like that is a closed concentric circles spheres as it's already given. So the outer part is this is dia is d2 is equal to 60 mm and T2 is equal to 42 degrees Celsius, and this is the inner emissivity is equal to 0.01. Sorry, did something wrong. Yeah, so this was for the later question, sorry. So F so this is D2. D2 will be is equal to 1.2 meter. T2 is equal to 300 Kelvin, and emissivity 2 is between 1 and 0.0. F12 is given as 1, like it's 1, right? And the for the inner surface, this is the inner surface, this is T1 is equal to 0.8, T1 is equal to 400 Kelvin, and epsilon 1 is equal to 0.1, 0.5. So for the first part, when for the first part we need to just form the resistance diagram. So if we form the resistance diagram, this is EB2, this is EB1, this is J1, this is J2, this is 1 minus epsilon 1, epsilon 1 E1, this is 1 minus epsilon 2, so this 1 minus epsilon 2, epsilon 2 E2, and this is for the view factor, 1 upon A1 F1. This formula we already know. Yeah, we have done it several times. Now for the first part, we'll just assume it as a black body. So what we will do, we'll just calculate Q12. This will be A1 F12 following Stephen Boltzmann's law, 2 to the power 4. Right. So this will be is equal to A1 is pi into 0.8 meter whole square into F12 is 1 into sigma is 5.678 10 to the power minus 8 into this is watt per meter square Kelvin to the power 4 into 400 Kelvin to the power 4 whole to the power 4 minus 300 to the power 4 Kelvin to the power 4. This will come out to be 1995 watt. For the second part, if it is considered as a diffuse gray surface, then Q12 is equal to sigma A1. Sorry, this is malfunctioning. Just 1 second. So Q12 is equal to sigma A1 T1 to the power 4 minus T to the power 4 upon this will be 1 upon epsilon 1 plus 1 minus epsilon 2 upon epsilon 2 R2 upon R1 whole square. This is area, right? 1 upon 2. This is 5.67 10 to the power minus 8 into T1 is this is sorry, A1 will be there. A1 is 0.8 pi 0.8 whole square into T1 to the power 4, that is 400 to the power 4 minus T2, that is 300 to the power 4. 1 minus epsilon 1 is 0.5 plus 1 minus 0.05. This is 0.05 0.4 upon 0.6 whole square. Yeah. Now this is equal to will come out to be 191 watt. For the third part, D2 is now given as 20 meter, and it follows that Q12 is equal to 5.67 into 10 to the power minus 8 into area is pi into point. This will be same, right? The inner dia. This is 400 to the power 4 minus 300 to the power 4 upon 1 upon 0.5 plus 1 minus 0.05 upon 0.05, 0.4 upon 10 whole square. So this is 983 watt. Yeah, so this question is done. You mark like which option is correct. For the first question, option A is correct. For the second question, option D is correct. And for the third question, option which one? Option A. Option A is correct. So we'll proceed to the next question now. So a diffuse gray radiation shield of 60 mm diameter and emissivity is inner surface is 0.01 for the shield, and outer surface is 0.1 on the as it's given, and is concentrated with a long tube transporting a hot process fluid. The tube surface is black with the diameter, so we can consider that as a black body. Diameter is given as 20 mm. The region interior to the shield is evacuated, and the exterior surface of the shield is exposed to large room whose walls are given at this temperature and experience convection with air at 27 degrees Celsius. So radiation will be there with wall temperature 70, and convection will be there. Heat transfer coefficient is given, and air temperature is 27. So their convection will be there. Choose the closest value of operating temperature of the inner tube if the shield is maintained at 40 degrees Celsius. Shield temperature is also given. So we can clearly find out with Q total. So there will be total heat. There will be a summation of heat that is from radiation and heat that is from convection. So if we do a simple energy balance first, let me draw this for you. So this is inner D1 is equal to 20 mm, and this is equal to the heated tube A1, and this is A2 for the sheet. Now this portion is evacuated. Now this dia is 60 mm and T2 is equal to 42 degrees Celsius. Inner surface is it is malfunctioning. Just 1 second. This inner surface is 0.01, and this is epsilon. This is epsilon to inner surface, and this is epsilon to outer surface. This is 0.1. Now the temperature, this temperature is T2 is already given as 42 degrees Celsius. Yeah, I've already written that. What else left? Yeah, it's this surface epsilon 1 is equal to 1, right? Because we can consider this as a black body, and there may be a wall whose like here T infinity for the air that you need for the convection is 27 degrees Celsius, and H is 10 watt per meter square Kelvin. And this temperature, the surrounding wall is 17 degrees Celsius. Now if we perform the energy balance on this shield, then there will be this surface Q convection, and there will be Q radiation, and this is Q12. This Q12 is the net radiation exchange between the tube and the inner surface of the shield. So this is inner minus outer total energy exchange is equal to 0. This is Q12 minus Q convection, Q radiation is equal to 0, right? Now Q12 is an iteration that we can clearly find out from that formula 1 upon epsilon 1 a sigma T1 to the power 4 minus T to the power 4 upon 1 minus 1 upon epsilon 1 plus 1 minus epsilon 2I upon epsilon 2I D1 upon D2. So from this we can clearly calculate. So this will put in the main formula, and the rest this we can clearly calculate this. This will be we can calculate from sigma a sigma 2 naught a2 sigma from Stephen Boltzmann law T2 to the power 4 minus T surrounding to the power 4, this surrounding wall, and this is H delta T. There is T2 minus T infinity between the air and the outer surface of the shield. So we'll, if we put the corresponding values, then we can clearly get temperature. So I'll give you 5 minutes to solve this, then we'll proceed with the solution. I'll turn this screen off for some time as it is malfunctioning a bit. Okay. So we'll take 2 to 3 minutes to solve this, then we'll proceed with the solution. Okay, so let us solve this now. Connect the writing pad. So first minus q12 will be is equal to a1 sigma t1 to the power 4 minus t to the power 4 1 upon epsilon 1 plus yeah 1 minus epsilon 2 I upon epsilon 2 I d1 upon d2. Now, using appropriate rate equations for this Q convection and Q radiation in the energy balance equation, what we'll write now, we'll just put it in the main equation. So this will be A1 sigma T1 to the power 4 minus T2 to the power 4 upon 1 plus 1 minus epsilon 2I upon epsilon 2I d1 upon d2. Minus convection equation is simply T1 minus T2 minus T infinity. Now epsilon 2 naught is outer surface, so this is A sigma, this is A2 sigma T2 to the power 4 minus T surrounding wall to the power 4 is equal to 0. So now epsilon 1 is given as 1. Substituting the numerical values, a1 upon a2 is equal to d1 by d2 and solving for t1. So this will be simply, I'll be just writing. You can solve it back at your home into 5.67 into 10 to the power minus 8 into t1 to the power 4 minus 315 to the power 4 upon 1 plus 1 minus 0.01 upon 0.01 20 by 60 minus 10 into 10 into 315 minus 300 minus 0.1 into 5.67 10 to the power minus 8 into 315 to the power 4 minus 290 to the power 4 is equal to 0. So if we'll solve this, then T1 will get us 745 45 Kelvin. That means 472 degrees Celsius. Okay, now let's proceed to the next question. The end of the cylindrical liquid cryogenic propellant tank is free space and is to be protected from the external solar radiation by placing a thin metallic shield in front of the tank. Assume the view factor FTS between the tank and the shield is unity and all surfaces are diffuse and gray and surroundings are at 0 Kelvin. Evaluate the temperature of the shield and this similar question only. Choose the closest value of the heat flux at the end of the tank. You solve it by yourself. I am not gonna tell this. We have to here we have to do the energy balances again for that shield surface, like between at the surface of the shield we have to energy balance for the incoming radiation and the outgoing radiation. If we'll do, we can solve for this temperature and choose the closest value of heat flux also we can get from that. So I'll give you 3 minutes to solve this and we'll proceed with the solution because there is not much time left and we have many more questions to do. Okay. Let me connect that first. So for this question, first of all, if this is the surface, let this is the surface temperature, the heat that is coming, like the heat that is coming falling on the surface, it will be absorbed. Alpha will be absorbed by the surface, that will go inside, and this is the emission of the surface, that is the emissive part. This is epsilon 1 of black body. Now this is QST is the heat, that is the flux that is exchanged between the cylinder and the sheet. Now alpha is GS minus minus epsilon 1 EBTS minus QST double dash is equal to 0. Now both shield and tank are considered as two surfaces, large and parallel plates. So QST will be what? This will be sigma Ts to the power 4 minus Tt to the power 4 1 upon epsilon 2 plus 1 upon epsilon T minus 1. So this will be alpha Gs if it put in the main equation minus epsilon 1 sigma Ts to the power 4 minus sigma Ts to the power 4 minus T1 to the power 4 upon 1 upon epsilon 2 plus 1 upon epsilon T minus 1. This is equal to 0. Now Ts is equal to, if we solve for Ts, this will be is equal to alpha S Gs plus sigma Tt to the power 4 upon 1 minus epsilon 2 plus 1 minus epsilon T minus 1. This upon sigma epsilon 1 plus 1 upon epsilon 2 plus 1 upon epsilon T minus 1. So this whole will be 1 by 4. So this is equal to 0.05 into 1250 watt per meter square plus sigma 100 to the power 4 upon 1 upon 0.05 plus 1 upon 0.1 minus 1 upon sigma 0.05 plus 1 upon 0.05 plus 1 upon 0.1 minus 1. So this is equal to 1, this 4 to the power 1 by 4 is equal to 338 Kelvin. So this is the first part. For the second part, choose the closest value of the heat flux at the end of the tank. So closest value for the heat flux at the end of the tank will be, heat flux from the tank can be determined from this equation that we already found, this equation. So we'll just put all the values. So this is 5.67 10 to the power minus 8 into 338 to the power 4 minus 100 to the power 4 upon 1 upon 0.05 plus 1 upon 0.1 minus 1. So this will come out as 25.3 watt per meter square. Yeah, so let's proceed to the next question now. It's already 9:22, so we'll just fasten it up. So for the question number 5, a cryogenic fluid flows through a tube of 20 mm in diameter, the outer surface of which is diffused and gray with an emissivity of 0.02 and temperature of 77 Kelvin. The tube is concentric with a large tube of 50 mm diameter, and the inner surface of which is diffusion gray with emissivity of 0.05 and temperature 300 Kelvin. The space between the surfaces is evacuated. Determine the heat gain by the cryogenic fluid per unit length of the inner tube. Yeah. So same, only similar fashion. So if the thin wall radiation shield is introduced in between the diffuse and gray with emissivity of 0.02 on both sides and inserted in the midway, the inner and outer surfaces, calculate the change in heat gain per unit length of the inner tube. So it's very easy. We have already solved many questions based on this type. So I'll give you 3 minutes to solve this and then we'll proceed with the solution. I'm going out. I'll be back in 2 minutes. Yeah. You try and solve this problem on your own. I'll be back. Let me connect the writing pad. So for this problem, the first part is it is a cryogenic chamber. The internal dia is 20 mm and temperature is 770 Kelvin and epsilon I is 0.0. This is the cryogenic fluid in tube, and this is the outer dia is 50 mm, temperature is 300 Kelvin and epsilon is equal to 0.05. This is the first part without shield. So this is no shield. So let us do this part first, and for the second part there is a shield also in between. This is a shield. So this shield is diameter is 35 mm and epsilon is 0.02. This is the shield. Okay. So now this is one resistance, this is second resistance, this is third resistance. EB naught, this is EBI, this is Q, this is inner side tube, and this is the outer side. So the first this is the outer side. So from the outside is coming to the inner side, right? So this is the inner side. This is epsilon I EI. This is 1 upon AI Fi naught outer. This is epsilon naught for the outer surface, A naught epsilon naught. Net heat gain per unit tube is minus Q1 dash is Q naught 1 upon L. This is E P naught minus EBI upon 1 minus epsilon naught upon epsilon pi D naught plus 1 upon pi di Fi naught plus 1 minus epsilon I epsilon 1 pi di. This is also epsilon I pi di. Now this is area is equal to pi dl. Now Fi naught is equal to 1 and EB, that is EB is equal to sigma t to the power 4. So minus Q1 dash is equal to 5.67 into 10 to the power minus 8 into 300 to the power 4 minus 77 to the power 4 upon 1 minus 0.05 upon 0.05 pi 50 into 10 to the power minus 3 plus 1 upon pi 20 into 10 to the power minus 3 into 1 plus 1 minus 0.02 0.02 pi into 20 into 10 to the power minus 3. This is meter inverse. So this will be is equal to 457 121 plus 15.9 plus 779.8 meter inverse. So this is 0.501 watt per meter square. For the second part, shield will also be introduced in between. So this is 1, 2, 3, 4 and 5 resistance. So this is E naught, EB naught, and this is EB inner side. This is 1 minus epsilon I and epsilon IA. This is 1 upon AIFI shield. 1 minus, this is for shield, epsilon S AS. This is for the shield and outer surface, FS naught, and this is for the outer surface. This is done. Now this will be EB naught minus EBI. So this is summation of RT. This is FIS and FS naught is equal to 1. That is for sure. It's already given. And this is 457. We already know about this part. This EB naught minus EBI. We already found this out earlier. So this upon 121 plus 121 is for the first part. For the second part, we don't know, so we will write this up 35 into 10 to the power minus 3 into 1 plus for the third part also 1.0.02 for the shield. 0.02 pi 35 into 10 to the power minus 3 plus for the shield and the outer surface, this will be 15.9 plus 77 9.8. This is M inverse. So this will be 457 upon 121 plus 9.1 plus 891.3 plus 15.9 plus 779.8 meter inverse. This is equal to 0.251 watt per meter square. Let us do like now what we need to find out. We need to find out the reduction in percentage. So Q1S with shield minus Q1 without shield upon Q1 without shield, I without shield, right? So into 100. So just 1 second. Yeah. So now so if we will write this up, okay, you just check the video for the solution of this, cause this the writing pad is malfunctioning. So this will be the reduction in the reduction in the radiation will be with radiation shield. We'll just simply find out without shield, with shield minus without shield upon without shield into 100%. So this will be is equal to 0.251 minus 0.501 upon 0.501. So this will be into 100%, that is minus 49%. So this is the answer. So I'll proceed to the next question now. So this will last question for today. After that we'll just end the class because it's already 9:40. So I'll give you 2 minutes to solve this, then we'll proceed to the solution. Okay. Okay, so for this problem, we simply will be calculating the heat loss by convection first, and that will be just one second. This question number 6, right? So for the heat loss for convection from both side of the plate, it will be 2HA delta T, and that is 2 into 2y, because both sides of the plate. So 2 into 87.5 into pi by 4 into 0.04 square into 295 minus 290. This is equal to 1.1. Now, for most of the solid, the transmittivity is 0. Uh, so, transmittivity, if we find at 0, the energy lost by convection will be is equal to the energy lost by radiation in this case. So, the energy lost by reflection will be is equal to reflection will be is equal to 2 minus 1.1. So 2 is the radiant energy, so the radiant source rate, so this will be 2 minus the loss by reflection, loss by convection is 1.1. So just one second. So the energy that is lost by reflection is 0.9 watt. So the reflectivity will be is equal to the energy that is lost by reflection upon the total energy, that is 0.9 minus upon 2 is equal to 0.45. This total energy minus loss by convection, so this will give what? This will give the energy lost by radiation. So the energy lost by radiation through reflection only. So this as we are considering reflection only is happening here. So the reflection is energy lost by radiation upon the total energy is 0.45. So we have 4 more questions left, but time is already out. So it's already 45 minutes extra we have taken. So what we'll do, I'll just give you all the 4 questions left, and I'll also attach the answers of this question along with the PPT. You can check it last, because PPT will already be uploaded in the sheet. And in that PPT, I will at last attach the answers for the rest of the 4 questions, and you can solve it back at your home. Okay, so this is the first question, the second question, the third, and this is the fourth. So I'll be attaching the answers of this question number 7 to 10 along with the PPT. And also the video will be uploaded into the YouTube section. You can check there, and whatever doubts you have, if you're having any doubt, you can directly contact to me. I'll try and solve your doubts. So thanks for being here, and as this was the last class, whatever doubt I'll solve you through I'll solve you for you through the mail. You can take my mail ID from the NPTEL section. You can mail them up, and you can ask them for my mail ID. We'll give it to you. And yeah, I hope you have enjoyed the sessions, and I hope this problem solving sessions have helped you in developing the problem solving ability in this heat transfer. Okay, so it was very enjoyable to teach all of you, and with this note, I'll end today's session and the last session as it is for this course. uh, I'll meet you guys, hope, in some other session of NPTEL. So bye guys.